Astronomers have found that the universe is filled with gravitational waves with very long wavelengths. What caused this? The most likely cause is collisions between supermassive black holes, but we can't rule out more unusual ideas. Today's public discovery demonstrates that spacetime's large ripples consistently compress and alter shape. Launched in 2015, LIGO was the first experiment to detect echoes from colliding black holes. These gravitational waves bear a resemblance to those echoes. But while LIGO's waves may move a few hundred times a second, it could take years or even decades for a gravitational wave to move at the speed of light. The discovery has given us a new way to look into the universe and may reveal things we didn't know about before, like how black holes with the mass of billions of suns spin through space, or even stranger, but still hypothetical, celestial spectres. "It's beautiful," said Chiara Caprini, a theoretical physicist at Switzerland's University of Geneva and CERN, who wasn't directly involved with the work. A new era of universe observation has opened up. 4 teams in the US, Europe, Australia and China worked for over a decade to achieve these results. In a coordinated data release today, the team showed proof of a background hum of gravitational waves found by watching changes in the beats of objects called pulsars that are too regular to be real. Gravitational waves with long wavelengths move through our galaxy and bend space around us, which changes when a pulsar's pulses arrive. For decades, they had to figure out how the arrival times of dozens of different pulsars related to each other to pick up the signal. Stephen Taylor, an astronomer at Vanderbilt University and head of the North American Nanohertz Observatory for Gravitational Waves, NanoGrav team, said, "I had butterflies when I first saw this. I'm so excited we can finally talk about it." The NanoGrav team mostly used the Green Bank Telescope in West Virginia, the Very Large Array in New Mexico, and the Arecibo Observatory in Puerto Rico to do their work. These go from left to right. Gravitational waves most likely come from pairs of very large black holes spiraling around each other in merging galaxies. However, cosmic strings, loops of energy, could create holes in space-time, causing something entirely different and strange. A theoretical cosmologist from the Autonomous University of Madrid named Juan Garcia Bellido said, "It's fascinating to find the first hint of background gravitational waves." He wasn't involved with the work, but said, "It's really Nobel Prize-winning research." You can start this discovery story in 2 different ways. The first one is with Albert Einstein, as always. His general theory of relativity, which emerged in 1915, said that things like black holes and stars float on an ocean of spacetime. These objects' movements would cause gravitational waves to ripple through this ocean of spacetime. Another place to begin the story is in 1967 with Jocelyn Bell, a graduate student from Lurgan, Northern Ireland. She saw a strange signal in space that happened every second through a radio telescope she helped build near Cambridge, UK. Later, she and other astronomers figured out that these signals came from pulsars, the rapidly spinning cores of dead stars. Some spin very quickly these days and send out regular radio wave pulses hundreds or thousands of times per second. Due to their regularity, pulsars are useful for keeping track of time in the universe. In 1983, astronomers Ron Hellings and George Downs from the United States came up with a new way to use them. If gravitational waves were pulling and stretching spacetime, that would change the time the pulsar's radio flashes arrived. It's important to look at many pairs of pulsars and compare how long their time delays are. NASA's Gravitational Wave Detection Working Group Chair, Sarah Vigeland, said, "If they're close together in the sky, they'll both be early or late." Vigeland is an astrophysicist at the University of Wisconsin-Milwaukee. As you pull them apart, they become out of sync, but in a way you can predict. Pulsar timing arrays such as NanoGrav use many radio telescopes to monitor many pulsars over a long period to catch these changes. To find gravitational waves, LIGO and other Earth observatories look for tiny changes in the relative lengths of their 2 arms. These projects are their cosmic cousins. The arms of LIGO are each 4 kilometers long. On the other hand, pulsar timing arrays use the distance from Earth to each pulsar to form an arm that is hundreds or thousands of light-years long. What we've essentially done is hack the entire galaxy to make a giant gravitational wave antenna, he said. Because they are farther away, pulsar timing arrays can pick up on different gravitational waves. LIGO can detect high-frequency gravitational waves, which occur when black holes the size of stars orbit each other tens or hundreds of times per second before merging. Pulsar timing arrays, on the other hand, can pick up on events that happen over years or even decades. Pulsar timing arrays need data from many years ago because you can't see a single wave in just a few months if it takes 10 years to pass by. Out of the 4 groups putting out data today, Nanograv is the most sure of its result. The project began in 2007 and mostly used the Green Bank Telescope in West Virginia and the Arecibo Radio Telescope in Puerto Rico. The Arecibo telescope collapsed in late 2020, close to the end of Nanograv's 15 years of data collection. Taylor said, "We're still sad about the loss of Arecibo. We have also set up pulsar timing array projects in different parts of the world. The 4 teams work together to make the International Pulsar Timing Array and plan today's announcements. However, they still need to do a joint analysis of the data." "It's complicated," said Andrew Zick, an astronomer in Australia who works for the Commonwealth Scientific and Industrial Research Organisation and is part of the Parkes Pulsar Timing Array team there. "We're ready to move towards being a more unified thing." In 2020, Nanograv released the first data from 12.5-year-old observations. These revealed a faint indication that gravitational waves were affecting the pulses of approximately 45 pulsars. They've added more years of data from almost 24 more sources, and the pattern is clearer. Vigeland said, "It really stands out to us." Scott Ransom, an astronomer at the National Radio Astronomy Observatory and one of the founders of Nanograv, described inconsistencies in time that are a few hundred nanoseconds wide. They are sure they can find the gravitational wave background because of the Hellings-Downs curve, a pattern in the data. That's the definitive evidence of gravitational waves. Over 25 years, the European team watched 25 pulsars with 6 telescopes and discovered similar signs of time delays. They are still figuring out what their results are, though. "They are very sure of themselves," said Michael Keith, an astronomer from the Jodrell Bank Centre for Astrophysics on the European team. The Chinese team has been looking at 57 pulsars for over 3 years, whereas the Australian team has looked at 32 pulsars for 18 years. What's making these waves, then? Supermassive black holes, which are millions or billions of times the mass of our Sun, are most likely the source. Massive galaxies like the Milky Way. When 2 galaxies collide, which does happen sometimes, the supermassive black holes at their centres may start to orbit each other. They move around at a very slow speed, causing ripples in spacetime. Keith said, "Gravitational waves are coming out if there is a rotating mass distribution that isn't symmetric. This could be something small, like a pen that spins. Supermassive black holes can hear these waves when they spread out through space on large enough scales." More researchers are working on Nanograv. Sarah Vigeland is an astrophysicist at the University of Wisconsin-Milwaukee and chair of Nanograv's Gravitational Wave Detection Working Group. Nanograv can't yet tell the difference between different sources of gravitational waves. Instead, the team has found proof that all low-frequency gravitational waves have a background hum. It's like a buoy moving back and forth in a busy harbour. It can't tell the difference between the wakes of different boats, but its movement can show that big things are cutting through the water. Supermassive black holes are not the only potential cause of the background hum. The idea of cosmic strings is another one. In the 1970s, it was first thought that cosmic strings would be space-time cracks caused by the universe's expansion. The cracks would send out gravitational waves as they spun in loops. The cracks would emit gravitational waves. One supporter of cosmic strings is John Ellis, a theoretical physicist at King's College London and CERN. The idea behind cosmic strings is that you have some extension of the standard model of particle physics, in which, in addition to point-like particles, you can get strings of energy stretching out across the universe, Ellis said. Those strings of energy can move around and collide, creating loops of string that eventually collapse by emitting gravitational waves. Even though the idea is a bit far-fetched, What Nanograv and the other teams have seen fits what we know about cosmic strings. Astrophysicist Patrick Brady from the University of Wisconsin-Milwaukee said they'd be moving around all the time, and every once in a while they'd crack like a whip and send out gravitational wave bursts. That could mean strange physics is going on beyond the standard model if the pulsar timing arrays don't see individual sources start to show up in their upcoming data. Cosmic strings will give you a much smoother signal, he said. However, supermassive black holes are currently the most likely explanation, even though we can't rule out strings and other strange things. From an Occam's razor point of view, we know galaxies merge, and almost all galaxies have supermassive black holes, said Ransom, so we think it's probably most likely that the signal we're seeing is from supermassive black holes. But we could be wrong. Find a group of supermassive black hole pairs. For example, what happens when two supermassive black holes in orbit get pretty close to each other? There were reasons to think they would keep rotating around each other forever instead of merging like smaller black holes do. Caprini called this the last parsec problem. A parsec is 3.26 light-years across. A population like this would change how we think about how galaxies have changed over time in the universe. It would mean that at the centre of some galaxies, there are massive black holes that are not alone, Caprini said. By studying the history of the universe, we can learn how and how often galaxies collide. To do this work, we would have to find individual pairs of supermassive black holes, which is impossible yet. However, individual sources may become clearer as more observations are made and the data from the different teams are combined over the next few years. This could help astronomers find binary supermassive black holes in space and time. Bright individual sources will start poking above this background hum, said Maura McLaughlin, an astrophysicist at West Virginia University and one of the group's founders. We can say that there is a supermassive black hole binary with a certain mass in that direction. We will learn a lot about how galaxies merge. Thanks to these projects, astronomers now have a new way to study the universe. Brady compared the rise of gravitational wave astronomy to Galileo's first look at the sky through his telescope. We now know that space-time ripples surround the universe, and an ocean of gravitational waves is waiting to be discovered. Could there be more than one universe, or is it just one universe? In many areas of physics, there are reasons to believe that there may be other universes that we can't see and have different natural laws. Theoretical physicist David Kaplan talks with Stephen Strogatz about the mysteries a multiverse would solve. The universe should include everything that exists, but new ideas in cosmology, particle physics and quantum mechanics suggest that there may be other universes that we can't see with different laws of nature. Many physicists think that the existence of a multiverse is a likely way to explain some of the biggest mysteries in science. In this episode, Stephen Strogatz discusses, do we live in more than one world? People know they live in their little bubbles, whether with their family, friends, hometown, or even at work. Animals also live in their own little bubbles. For example, fish live in different lakes, rivers, or oceans. You won't find them in ice with microbes or in the sky with birds, even though ice and water vapour are both forms of water. Could the universe be the same way? We may not see it that way. The idea that we might live together in a multiverse is hard to imagine. David Kaplan, a theoretical physicist at Johns Hopkins University in Baltimore, doesn't rule out this possibility, no matter how unlikely. His work delves into the theoretical foundations of the standard model of particle physics and cosmology, examining the possibility of a multiverse. He also played a significant role in the 2013 documentary Particle Fever, which chronicled. Before we discuss the multiverse, how would you describe the universe? People often talk about the observable universe, the part of the universe we can reach. However, the size of the universe limits our view of it. When our universe first formed, it was so dense and hot that light couldn't pass through it. This means that the observable universe is the farthest point in time, and light left that part of the universe much earlier. Plasma, also known as the early universe soup, trapped light when the universe was smaller, hotter, and denser, preventing it from travelling in a straight line. When the universe grew and cooled enough for light to travel from one place to another across the universe, it left what we now call the surface of last scattering. This is why we see a surface in all directions when we look out into space. There is a lot of uncertainty about the multiverse and the universe's beginning. For example, people often say, at the Big Bang, you created time and space. And they're right. However, as you approach densities of order, a phenomenon known as Planck energy emerges, implying that a geometric universe theory cannot explain gravity. That doesn't mean there weren't other times and spaces in the past. Could time go back indefinitely? Is there a different name for what we call time? Yes, there is. We don't know. We are still determining what this turns into at very low energy densities when you get to a level of energy where general relativity doesn't work. It's not just a mathematically sound statement when people say that time and space appear independently. It's also a hopeful way of condensing space and time. And if you don't have anything, it's hard to guess when something will appear because there's nothing there. Now, what is the multiverse? The multiverse, as it appeared in Particle Fever, was a use of the multiverse. It was the idea that, in a seemingly mundane way, if the universe is infinite, or much, much bigger at least, than the part we see, the observable part, then the laws of nature in different patches may differ. You don't even need the deep underlying laws to be different. It would help if you had some of the parameters changed. The numbers describe the vacuum energy in that part of the universe. What are the values of various background fields, such as gravitational fields or other fields, in those specific regions of the universe? And if those things differ in different places, they will have a different expansion history. The universe in that region will expand based on what's in the universe and the interaction strengths of the stuff in that part. Therefore, it's possible to create radically different universes, each with a slightly more mundane explanation of how the laws may vary from one location to another, or even the universe's composition in each of those locations. A simple way to think about the multiverse is to say that there is only one universe, and each part has its own rules that govern how life appears. But if you go far enough away, further than light could have travelled in the age of the universe, there are places where the rules are different, the parameters are different, and the history of the universe's expansion is completely different. No stars or galaxies could have formed in those areas, and nothing exists. We have laws, initial conditions, a description of how the universe works, and instructions on experiments on Earth. The laws stay the same over time, no matter where the experiments happen, because our galaxy moves quickly in the background. The laws are stable here, but only a short distance away. Stars may or may not form, and chemistry may or may not work, depending on the type of. It's like how the speed of light and the amount of time the observable universe has been around are limited. We live in our patch, but who knows what happens in the other patches? We can't see them, by definition. But there's a good reason to believe in the multiverse, or many reasons other than this college dorm speculation. Can you tell me about those? For example, in physics, some mysteries inspired physicists to develop the concept of a multiverse. The standard model of particle physics is based on quantum field theory. Quantum field theory describes how particles interact at high energies in simple and complex systems. It also describes the internal properties of particles, such as the magnetic moments of electrons and the strong force and confinement of nuclear matter. This theory gives us a complete picture of how all matter works. It also includes a list of parameters that indicate the strength of the electrical force between the electron and the proton, while other numbers indicate the likelihood of different particles scattering. Some of those parameters make a lot of sense. You can put in host numbers, figure out quantum corrections, or look at situations where the background is slightly different, and those parameters don't do anything strange. The standard model has two strange numbers. One of them is the Higgs boson's mass. We measure all other fundamental particle masses using the mass of the Higgs boson as the standard. For example, the mass of the electron is equal to the mass of the Higgs boson. The top quark's mass, which is the heaviest quark, is equal to the mass of the Higgs boson. The weak force boson W is equal to the Higgs boson's mass. So the Higgs boson controls one physical mass scale out of all the particles in the standard model. You chose that scale. We measured the Higgs mass, the masses of the other particles, and how they interact with the Higgs. This lets us try different ways of setting that number. Let's look at a quantum field theory with the Higgs and all these other particles. If you try to guess what the Higgs mass should be, what the Higgs' usual mass would be in this quantum field theory with these particles, you get infinity, which doesn't make sense. But you say, okay, that's fine. I reach infinity because I think there are no new particles with very high energies. Quantum fields and theories can't work without considering quantum fluctuations when determining physical parameters. Now you know what your theory should be based on. If you want to know about a physical state, any measurement you make in quantum theory includes all of its quantum changes. When you look at the Higgs case, the quantum fluctuations would be infinite if the standard model was up to infinite energies. We need to revise the standard model for energies that never end. When we add the rate of gravity to the standard model, we introduce a new type of energy known as the Planck mass. But once you reach that energy level, there may be many other particles, new symmetries, or other things that no longer add to the Higgs mass. It has come to an end. Everything is fine. If your model works with any amount of energy, you will reach infinity. You then stop these models and say, okay, there will be new particles with a certain mass. Above that, let's assume they don't add to the Higgs. These are the times when quantum fluctuations add to the Higgs field. Regardless of your belief in the standard model, all energy levels influence the Higgs mass. This means that these random high energies, or masses, contribute to the Higgs mass. This should connect the Higgs boson to physics we don't know yet. There should be some new physics at high energies, and the Higgs mass should be about that large. In other words, the discovery of the Higgs and its mass should reveal more physics beyond the standard model. To explain this, you reverse the order of the ideas. You say there is unknown physics above the Higgs and that energy affects the Higgs mass. You're saying, oh no, if I measure the Higgs, it will come with all this new stuff. Because the Higgs mass is not infinite, it's finite. That means that I will see what we already know on one side when we find it. But since it's a borderland, things will be on the other side of the line. Because it is new to physics, we will be thrilled to find it and measure its properties. That made people study what was on the other side of the border for decades. What new idea says that the Higgs mass is finite instead of infinite? The theory should make sense now that all the quantum changes have been considered. As a result, it should encompass a wide range of concepts. Some people have also suggested symmetries, sometimes called supersymmetry. We could also consider the Higgs as a composite particle. While we know that the proton consists of quarks, the Higgs could potentially consist of other elements. There is stuff inside, and we can see other fundamental particles when the energy is very high. In this case, it could even be about to end itself. When the energies are high, the description is very different. We discussed and studied these kinds of quantum field theories, wondering if they could explain what we observed. The Higgs mass is nonsense, but it's a statement that a new theory exists above it regarding mass and energy. We can even develop ideas for that theory that solves the problem with the Higgs mass. The LHC, the Large Hadron Collider, gave people hope when it turned on. That's when they found the Higgs and some other new things. We'll call them degrees of freedom, which means the number of ways a particle can move or interact with other particles. There is a difference between the masses of these other particles and the Higgs. We look at its internal structure properties, which show that the Higgs doesn't have a fundamental form. But that might not be the case. The Higgs mass should have many properties but might be small by accident. That would be on edge, but all the new particles that have been added to make it finite mean that when those quantum fluctuations add to the mass of the Higgs by some terrible accident, they cancel each other out so much that the Higgs mass is incredibly small compared to where the edge of new physics really is. Because the Higgs is so sensitive to changes in quantum numbers, physics refers to it as a fine-tuned situation. This means that there must be an accident. The other world, the new physics, the new particles, and the new laws governing how the Higgs behave have yet to learn about the low-energy, low-lying masses. This is why it wouldn't choose an energy scale for the Higgs that is arbitrary light compared to all the dynamics of the new physics. For example, at 200 megaelectrons, the strong interactions between quarks get stronger on a certain energy scale. At that point, the interactions between the quarks are so strong that we can't pull them apart. What is the proton's mass, you ask? It's made up of quarks. That amount is about 5 times bigger. How heavy is a neutron? That amount is about 5 times bigger. What are the masses of the different mesons made up of quarks and antiquarks? The mass is several times that of quarks and antiquarks. It is less heavy than the previous one but has about half as much energy. All particles live in this range of energy, from quarks to the nuclei in atoms. Using that scale of energy is all new physics. We think the same thing. Whatever controls the dynamics of making a Higgs boson will be at that energy scale. It doesn't matter where it comes from. It could be the lightest thing in the mess. There is no way that Higgs could be near the Sahara Desert. There could be something out there. We get hints of it from time to time. But, it's usually just a mirage. That was really in the 1970s, between the mid-1970s and late 1970s, when Ken Wilson said that the standard model with just the Higgs is awfully fine-tuned and that there's an infinite instability in the calculations or the contributions to the Higgs mass unless you say there's some energy where there's new physics. That made people start to think about ideas. One idea was that there might not have been a Higgs at all. Instead, Higgs's behavior was a new type of strong confining group. This theory in particle physics explains the strong force, one of the 4 fundamental forces in nature. This group could do everything you expect the Higgs to do, like provide particle masses. Building those models was a lot of work. Supersymmetry was considered a way to protect the Higgs as long as there were partners or the rest of the zoo to keep the Higgs mass stable. That happened in just a few years, from 1978 to 1981. Those were the first thoughts behind these kinds of theories. Later, even stranger ideas started to come up. At the start of the 2000s, some people thought the Higgs scale would be the highest energy level. The Planck scale of quantum gravity is not 17 orders of magnitude heavier than what we think the Higgs is. It's right on top of it by some trick. But to do that, you have to say that space has more dimensions than now. This is a bit crazy. The extra dimensions of space make gravity behave in a very strange way. It makes it strong at a much lower energy level than the Planck scale. It is weaker, though, because it dilutes so much in the extra dimensions. It only looks strong when it has a lot more energy. But we were able to solve the problem using numbers. In terms of physics, though, it didn't help because we still needed to know about quantum gravity. We still don't know how or why the Higgs could have come from this theory, but we do know what it means. Despite its lack of satisfaction, it remained an intriguing possibility that the test bench couldn't rule out. Different people could explore that possibility in very different ways. The real intellectual motivation I hoped for, but never really knew what it was, is now clear to me. I've heard fine-tuning a million times, but I've never been sure what it meant. As good as the Higgs is, and as useful as it has been to physics, it has caused a lot of trouble in this way. This fine-tuning shows what its properties are. Will fine-tuning, also known as the enigma or multiverse, help solve this problem? Is that the plan? Making small changes doesn't mean that the theory is wrong, it just says that it smells bad. You say, I think it does this and that. You tweak some parameters by 1 part in 1034, which you would need to do if the new physics is at the Planck scale. This is done to get rid of all the different parameters. This ensures that the Higgs have a mass very different from the scale of the physics that created them. It's possible, but that clue should help us figure out what else is happening. It removes infinities. The Higgs is composite. There are no high energy scales, not even in extra dimensions. That's when all these other theories said, oh no, there could be new particles right around the Higgs mass. However, another possibility is that it has undergone fine-tuning, leading to a different explanation. You might think, well, maybe we're thinking too narrowly. This means that when we talk about the laws of nature, we do so in a very strict way. We say that the part of the universe we've seen has these fixed, unchanging, uniform laws of nature that apply across space. That's all. We need to fine-tune the Higgs mass due to its peculiar nature. Some people also call it the multiverse. The parameters and factors determining the Higgs mass are different in different parts of the universe. Any change in any part of the universe would affect the Higgs mass and properties, because it interacts with almost every part of the Standard Model in some way. The Higgs mass is naturally very heavy and includes almost everything in its family, including the particles, excitations, and dynamics that made it. Based on the Standard Model of the universe and nature, the Higgs mass is always close to that energy scale. This is a much higher energy scale than the one we've seen in experiments. On the other hand, the Higgs mass will vary in different places because the laws of the universe are not the same everywhere. And if the universe is big enough, there should be places where the Higgs mass is different from what it should be. The quantum fluctuations that add to the Higgs mass sometimes cancel each other out by accident. The Higgs mass could be exponentially smaller than it should be in some parts of the universe. This could happen by accident. For that to happen by chance, there would have to be infinite universes. But no one knows how huge the universe is. How do you know how the parameters change? In that case, this is a possible outcome. Then you must ask, why do we live in an aberrant universe with crummy cancellation that makes it very hard to discover anything? The answer is that the Higgs or any other underlying physics has much more power over whether or not we exist. Instead of calling it us, we can talk about it as a structure rather than making it personal or about people. Let me give you a very simple example. We don't live in space, we live on Earth. Why don't we live somewhere empty? Indeed, we are an integral part of the Earth, having formed from the same elements that gave rise to it. It also shaped us. Why are we so close to the Sun? We place the Earth close to the Sun. Why do we live close to the Sun? Since living things don't normally reside in places with lots of energy sources, there needs to be a strong argument for why we choose to live on Earth instead of the 1060 times larger space that is the rest of the empty universe. We don't talk about the problem, though. Different parts of the universe follow different rules. When it comes to the Higgs mass, there may be no chemistry for a very large range of Higgs masses. This means molecules don't bind, so structures can't form in those places. It has yet to look into nature's rules and find all the possible underlying principles. In other words, you wouldn't tell me about a giraffe after I gave you the Standard Model. It's impossible to tell me what could happen in a chaotic, non-linear process, but it's at least the starting point. Something important needs to happen. For instance, you could think that the Higgs mass would have to be much smaller than the Planck quantum gravity scale for the structure to form normally without any black holes. You can formulate rules that allow for precise tuning of the Higgs mass's unique values. In those universes or parts of the universe, though, really strange things happen, like how stars and planets form and what lives on planets. This happens all the time in astronomy. You can count the stars and say, oh, this is how many stars I see, and this is how many of this type and this type of star. However, type A stars are very bright, whereas type B stars are very dim. Type B stars are difficult to see. It's possible to think that there are 20 times as many type As as type Bs, but type Bs are really hard to spot. So we have a bias in how we observe things. There are 1,000,000 times more type Bs than type As. I'm still making simple observations to determine how many stars there are. I need to get smarter about how I watch. Everything else, however, is in a realm I can see. The multiverse is a place that we can't normally see. However, the Standard Model setup and the formations in different parts of the multiverse may still introduce an observational bias. So far, we've been working on making the idea of a multiverse more interesting. But I wonder if I remember hearing the terms eternal inflation or bubble universes coming out of an inflationary cosmology scenario is another way to make the case for a multiverse. It's the easiest way to create a multiverse if it makes sense. The Higgs mass and the cosmological constant are the two parts of the Standard Model that make the idea of a multiverse possible. In our universe, we have seen a lot of evidence for this cosmological constant. As a result, the universe is expanding faster than usual. Not only is it known as dark energy, but the cosmological constant is also something in the Standard Model. It's also something that causes quantum changes. In this world, the cosmological constant could have been any number. Again, the Planck scale is the highest energy scale we can think of in physics and is well tuned. Getting that just right is like 1 part in 10^123. Something must cancel out for the cosmological constant to be nice and small in the new physics. To think about this, you have to be thankful to be alive. Though I'm not religious, I can see how tempting these kinds of thoughts might be for someone who is. Consider yourself fortunate. 2 remarkable events were required to occur. We had to make these numbers just right. Another reason for fine-tuning is that the statistical sample cannot include things in the distribution's tail. On the other hand, the items at the end of the distribution are necessary for life and structure. Not at all, because a supreme being wants life to exist, the numbers are what they are. You could think of it that way too. I'm not crazy about any model of the multiverse, but I also need a model of an all-seeing creator who can set these things up. They're hard for me because my day job is to figure out what's going on. They also don't have many teeth. Because it is the only energy density in the universe that doesn't decrease over time, it is known as a constant. The universe's expansion changes the amounts of matter and radiation, which are constant. The universe's contents drive its expansion. Everything else thins out, but the constant doesn't. This means that the cosmological constant wins and speeds up the universe's expansion at some point in its history. The universe grows faster than other kinds of matter because of a cosmological constant. In fact, most types of matter not only allow things to expand, but also tend to slow them down. Imagine the force of gravity drawing matter and radiation together. The analogy may be more accurate, but its purpose is to decelerate the growth. A cosmological constant, on the other hand, gives you the opposite sign. It acts to speed up expansion. It speeds up growth by the same amount as itself, which is why we call it exponential growth. As a result, when the cosmological constant becomes the universe's main energy source, it starts to grow very quickly. Nothing forms only if this occurs too early in the universe's history. Because the cosmological constant expands constantly, galaxies, stars, and other matter groups would be unable to form. Gravitationally weak things would not have formed in the early universe. Because of this, every structure in the universe is a major source of interesting and non-trivial things like life, stars, and in fact everything. It wouldn't have been possible to make those things if the cosmological constant was too large. You can alter other parameters to expedite the creation of those entities. However, the cosmological constant differs in different parts of the universe. Then, the expansion of those parts of the universe would be very different. Also, patches with higher cosmological constants would not have anything in them. This further diminishes the significance of living in a place where material possessions are a priority. Once the shape is formed, we must live where exponential growth starts. Let's look at our universe and the cosmological constants we know. The exponential growth would take over after 14 billion years, 140 billion years, or 1 trillion years. The cosmological constant would be the universe's main source of energy. Could our galaxy or cluster split up? The answer is no. In fact, things held together by gravity, like our galaxy, do better than the cosmological constant. So, because there is more matter in the galaxy, gravity is still more important on a local than a cosmological level. But exponential growth will break up things that don't have gravitational bonds. All that is required to form a structure is for the cosmological constant to take control. We live in a universe with a cosmological constant big enough to hold all other parameters constant. This means that matter had a chance to form. In other words, we might not have seen any cosmological constants, or they might have been zero. The cosmological constant is also zero for some strange reason. Galaxies would not have formed if the cosmological constant was 100 or 1,000 times bigger. There wouldn't have been time for the gravity-bound states that make up our worlds to form. Because of this, the universe would have no life and no interesting structure. Ultimately, the cosmological constant was very small and very large. The 1998 measurement served as a wake-up call, revealing that the universe's visible parameters, rather than deep energy or natural laws, could influence us. Then you might think, okay, maybe it's the same accident. This patch has a tiny cosmological constant because of an odd amount of cancellation. But that's not odd if the cosmological constant is different in 10 to 500 universes or patches. A lot of those patches would be empty, with no outline. Even the rarest parts of the universe could contain a much smaller cosmological constant. The cosmological constant is as large as possible without destroying or stopping us from forming because we're in the most populated part of the universe. In this way, the multiverse, the landscape of possible universes, is a statistical argument. We need to determine the priors and which parameters to change. Something interesting happens when you keep everything else the same and change the cosmological constant. The cosmological constant is close to what it would be in a normal universe with galaxies and life. When you think about all of this philosophically, it really blows your mind. We live in a world with this anthropic principle that dates back to, the 1960s. But it keeps getting more important. Most of the time, the anthropic principle was more obvious. In this case, though, it's trying to eliminate observational bias, which means we must remember that the measurements we're using are the ones we have access to. We're here to use a certain type of measurement or a certain range of parameters. Since the cosmological constant is hundreds of times bigger, we would not have been able to measure it. There would have been no structure, so it would not have been possible. Different particles make up a different life on a different timescale, one that lives long enough but not too long. That might be true. After that, you might ask, why aren't we living that life? If the entire argument about the existence of humans is correct, does it imply that atoms formed the first real structure? It's hard to tell the difference between scientific questions and questions about the universe's beginning. Physics is interesting because it gives us two main ideas: dynamics, which are nature's laws, and dynamic laws, which are differential equations that we use to find initial conditions. You can test nature's rules over and over again. However, we provide the initial conditions for you. We may receive false results if there is a significant error in the starting conditions due to the measurement process. They're historical. They rely on this aspect of the universe's history. From a bigger picture point of view, this might be strange or out of the ordinary. These thoughts are really interesting. Could you take a look into your fairy world? That's the end of it. What ideas about the multiverse, cosmological constants, the Higgs boson, and all of these ideas, especially the multiverse, would lead us into the field of physics? We should have addressed a wide range of topics. Look at how quantum mechanics interacts with the multiverse and the multiverse that lives in quantum mechanics. We still need to do more research, but the initial doubts about using the multiverse to explain parameters should remind us that we might only partially understand some things. There are also reasons we will never be able to explain the mass of the Higgs or the cosmological constant. On the other hand, that doesn't mean there isn't another better way to explain things. It makes physicists think of the scary part of their job. It's a game with many risks and rewards. It's also possible to think that a path will be useful for a long time, only to find that it leads nowhere. You might also want to know why it ends there. These physics ideas could affect people's choices about the importance of solving the cosmological constant problem. Why is it so small? But it has yet to help find a solution. There is an observable universe which is like the universe's boundaries. We can only discover a limited quantity within it if it has a finite lifespan. Also, every person has a limited time on this earth, and we may only be able to find all of nature's laws so many times. I have yet to fully accept the multiverse as a way to explain these things, but they make sense. I can still think about those problems in different ways, though. It raises the bar for the quality of the possible solutions I seek.